Hello. In this section we're going to further explore probability, and this time we're going to look at the probability of sequential events and as well as conditional probabilities. What happens if something has already happened to your sample space? And so let's go ahead and get started with part 2 of the lecture notes on chapter 14. So the first thing we want to look at is the idea of conditional probability. And we're going to look at that as well as the probability of different things happening all in a row. So conditional probability, I want to look at two examples and just show you the difference between them. So the first one says, what's the probability of rolling 2 dice and obtaining a sum that's an odd number? Now, in order to do these dice problems, what I always use is this sample space document. And it's board site, under course documents, not under course documents, chapter folders. Go to the chapters 13 and 14. And underneath the lecture notes is the sample spaces. And if you open that, the very top of it is rolling 2 dice. So if you look at that, and we want to know what's the probability of obtaining a sum that is an odd number, what you're going to do is you're going to say, okay, where do I get odd numbers? Well, I've got odd numbers here. A 1 and a 2 and a 2 and a 1 make 3. I've got odd numbers here across this diagonal. All of those make 5. And you want to keep looking at those until you get all of the ways that you could get odd numbers. All righty. So if we do that, let's go back to our sheet here. Whoops. In order to find the probability of rolling an odd number, we need the number of ways of getting an odd sum over the total number of possibilities. All right, and we've talked about this before. We know that when we're rolling 2 dice and we look at that sample space, there are 36 ways that the dice could come out. Then if we look at the number of ways of rolling an odd sum, well, there's 2 ways to roll a 3. You could have a 1 and a 2 or a 2 and a 1. There are 4 ways of rolling a 5. And you can look at your printout as we go. There are 6 ways of rolling a 7. There are 4 ways of rolling a 9 and 2 ways of rolling an 11. So when you add all that up, you get 18 out of 36, or 1/2 the time. All righty? Okay, the second question says, what is the probability of rolling a sum that's an odd number given, and here's a key word, given that the sum is greater than 6? So in other words, what we're doing is we're saying, what is the probability of rolling an odd number given, and I'm going to use this line to represent given that our sum is already greater than, greater than 6. Well, I go back over to my sample spaces, and I say that I know that I'm given that the sum is greater than 6. What that does for me is that says that everything that's less than 6 is not valid anymore, which is all of these, all of those, and all of these, okay? And it's got to be greater than, not equal to 6, so that knocks out all these ones that are equal to 6 as well. And here is our new sample space. So we've taken that sample space and we've altered it by saying that we know that the sum is already greater than 6. All right? And then we're going to look at what's left. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15, 16, 17, 18, 19, 20. 21 21 possibilities that are left. So when I go back to my when I go back and work on my probability, instead of having those 36 ways that I had up here, now I've only got 26 things, or what did I say, 21. 21 because we knocked a whole bunch out that had a sum that was 6 or less. And of those where we had a sum that was greater than 6, how many of them were odd? Well, the 7, and there were 6 ways to get a 7. The 9, there was 4 ways to get a 9. And an 11, and there was 2 ways to get an 11. So there's 12 out of 21 possibilities. So what this given does is it basically changes what our sample space is. So that brings us to the idea of conditional probability. We have placed a condition on what's happening. So the definition says we've got 2 events. Anytime we've got 2 events, and I'll call them E and F, then the probability of F given E, okay, so the probability of some event F happening, given that E has already happened, let's write that out, F given that E has already occurred. So that's what conditional probability means. Here's the notation we use for it, and it says find the probability of F given that E has already occurred. Now we've got a formula for that. The probability of F given E is the number of ways in which E and F both occur over the number of ways that E occurs. Or, like I like to think of it, take your new sample space, which is now E, and figure out the number of ways that F happens within that E. So let's look at another example of this. So it says, using a standard 52-card deck, find the probability that if you draw a card at random, it is a king, given that the card is a face card. So if we're looking at the probability of a king, given that it's a face, what that does is instead of dealing with the 52 cards anymore, we are now dealing with only the face cards. That's our new sample space. And remember, there are 3 face cards in each suit, so there's a total of 12 face cards. And the probability of getting a king out of those face cards, well, there are 4 kings. So that simplifies down to 1/3. Okay, let's look at one more dice problem. It says 2 events for the sum of the 2 dice for the sum of 2 dice are E, that they have a total that's greater than 9, and F, that the total is odd. We want to find the probability of E given F, and we want to find the probability of F given E. So take a minute and go ahead and come up with what you think it is. Pause this and see if you can figure out how that's going to work. All right. Hopefully you paused that and worked on it. And now let's go ahead and look at it together and see if we can come up with what this is going to be. So the probability of E given F is going to be, we're going to say, I'm going to start with the fact that I'm dealing with an odd total. Okay? So how many ways can I get an odd total? Well, if I look back up above, when I was finding the probability of an odd number, there are 18 ways of getting an odd number. So that is what my new sample space is going to be. It's going to be all the times and all the ways in which I can get an odd number. So that's going to be my sample space. And then my event space, or my event that I'm interested in, is that the total is greater than 9. So if the total is greater than 9, that means it could be 10, 11, or 12. So in order to have a total that's greater than greater than 9, the only things that are going to work with my sample space now, which is going to be the odd numbers, is going to be these 11. And there's 2 ways to get an 11, so my probability is 2 out of 11, or we could simplify that down to 1/9. If we switch those, all right, that switch is going to be important because if we're looking at the probability of F given E, that means we need to start with E, which means we're starting with a total that's greater than 9. All right, so there's 1 way to get a 12, there's 2 ways to get an 11, and there's 3 ways to get a 10. And then we want to know what's the probability that we get an odd, given that we already started with something that's greater than 9. All right, so what we're going to get for that is a number of ways we can get an odd, and the only odds that are possible are those 2 11s. So when we simplify that, we're going to get 2 6, or 1/3. So hopefully that makes some sense as far as what we're doing with the denominator. We're changing what we're starting from as our sample space. Let's go to the next page. And on the next page, we're going to use the table below to answer the following questions. And what we're looking at is we're looking at mono tests. So if you take a mono test and you have mono and it's a positive test, that happens 72 out of 140 times. If you don't have mono but you get a positive test, that happens 4 out of 140 times. If you have mono but the test comes back negative, that happens 8 times. And if you don't have mono and it comes back negative, that happened 56 times. So you did 140 tests, all right, of people. Some had mono, some didn't have mono. You had some positives and some negatives that came out. And here's what we're working from. So what we want to do first is we want to find the probability that a student chosen at random has mono, given that the test is positive. All right. So notice what that does. If we are given that the test is positive, then instead of dealing with all 140 tests, we're only dealing with the 76 positive tests. So the probability that they have mono and it was a positive test, well, there are 76 positives. And of those 76 positives, 72 had mono. Okay, so if we turn that into a decimal, 72 divided by 76, we get about 95.95. Or 95% chance. All right? So in other words, if the test is positive, it tells you about 95% of the time it's correct that the student does have mono. Now let's find the probability that a student chosen at random does not have mono, given that the test is positive. All right? So probability that they don't have mono doesn't, but they still get a positive test. Well, again, we've got 76 positives, and of those 76 positives, 4 of them did not have mono. So that comes out to about 5%. We call those false positives. Okay? They did have a positive test, but they actually didn't have mono. And lastly, find the probability that the test is positive given that the student has mono. So the probability that the test is positive given that the student does have mono. Well, again, we're going to start with how many students have mono, and there's 80 students total that have mono. So that's our new sample space. And of those who have mono, how many got a positive test? 72%. Okay? So that test is right about 90% of the time. Okay? So it comes out to be about 0.9. So hopefully that kind of helps you see how that condition is going to play into how we find our probabilities. The next thing we want to look at is the intersection of two sets. And if you remember from a previous lecture, we talked about the intersection of two sets being the probability of A, and here was our notation that we used, but we said the key word is both, or another key word is and. The probability of A and B, or probability of both A and B occurring. And the way we find that is we say we need to find the probability of A, and then multiply that by the probability of B, given that A has already occurred. Okay, so we're going to multiply those two probabilities. For example, suppose that we draw two cards without replacement from a standard 52-card deck. What is the probability that both cards are red? So the probability of a red and a red 1 and a red 2. Well, we'd start out with the probability of that first red occurring. And since there are 26 reds out of the 52 cards, that would be the probability of that first red occurring. Times, once that first red has occurred, now instead of having 52 cards, we're down to 51 cards because we are doing this without replacement. So our sample space now is 51 cards big. And of those 51 cards, well, we already pulled out one red. So there was 26, now there's 25 reds. All right. And then we could just go ahead and multiply that. 26 times 25 over 52 times 51. And you could simplify that, or you could turn that into a decimal. And it's about 245. All right. So the probability of drawing two red cards is right around 25%. Another thing that's often done when you're looking at multiple events is using trees to compute probability. So here's what I mean by that. A candidate for a driver's license is currently allowed to take a driving test 3 times before having to retake the preliminary written test. Some believe that candidates should only be given 2 attempts at the driving test before retaking their written test. Others believe that such a regulation is too harsh for those that now pass on the 3rd attempt. From past history, we know that 60% pass the driving test the first time, 75% pass on their second try, and only 30% pass on their 3rd try. So what I'd like to do is I'd like to set up a tree that kind of shows what's happening here. So what we're going to do is we're going to take this test. And the first time we take the test, we've got 2 things that could happen. You could either pass or you could fail. And the probability of passing is, let me put the pass and the failure. You could either pass or you could fail. The probability of passing is 60%. So I'm going to put 0.6 here. And the probability of failing, since these are complementary events, you either pass or you fail, would be 40%. If you pass, you're done. You don't have to go on. But if you fail, you take the exam again. And again, you either pass or you fail. On the second time through, 75% pass, which means that 25% fail. And then if you have to take it a 3rd time, again, you can either pass or you can fail. And this time, only 30% pass, and the other 70% fail. So there is our tree diagram. Now what I'd like to do is I'd like to use that tree diagram to answer a couple of questions. So let's go to the next page here. And here's the questions that go with this. So first, what is the probability that a candidate will fail the test the first time and pass the test on the second try? So what I want to do is I want to know what's the probability that the candidate will fail the first time and then pass the second time. So what has to happen is they have to do this first, and then they have to do that. So we've got an and here. Anytime we've got an and, we're going to multiply those probabilities. So what I'm going to get is they've got to fail first. So the probability of failing is 0.4. and then they've got to pass after they've failed, and the probability of passing after they've failed is 0.75. And when I multiply those, I will get 30%. So notice, 60% passed the first time, 30% passed on the second try. So how many have passed so far? 90% pass on first or second try. Alrighty. Now let's go ahead and use that tree again for one further question. What is the probability that a candidate will fail twice and pass on the third try? Well, that means they've got to fail and then fail again and then pass. And so I'm going to have to multiply these because these events all have to happen in sequence. And I've got an and between them. I've got to fail and then fail again and then pass. So the probability of failing is 0.4. Probability of failing a second time is 0.25. Probability of passing the third time is 0.3. And when I multiply that all out, I get 0.03. So that means 3% pass on the third try. So how many don't pass at all and have to go back? Well, if 90% pass on the first or second and another 3% pass on the third, that means 93% have passed, and that means 7% have to go back and do it again. All right. So even though the formula only has two things in it, we can go ahead and spread that out for even more of those. All right. Okay. So let's look at the idea of independent and dependent events. So the definition of independent events is if probability of F given that E occurs is equal to the probability of just plain old F, not even caring about E. And notice that makes sense because if the probability of F is the same as the probability given that E occurred, E didn't make any difference to the F, so we consider those independent. So we can say then E and F are independent. And likewise, dependent if the probability of F given E is not equal to the probability of F, then E and F are dependent. Okay. F depends on what happens to E. So let's look at a couple of examples here. Put this other page back behind. So the first example says, assume we roll a pair of dice. Are the following events dependent or independent? E, the total showing is greater than 9. F, the total showing is even. All right, so the probability of F, we want to know, is that equal to the probability of F given E. And what we're going to look at here is, what is the probability of F? The probability of F is that the total showing is even. So if we go back to our sample spaces here, the number of ways to get evens are, let's see, I could get it 1 and a 1, or a 1, 3, 2, 2, 3, 1. So I'm just going to count these up. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 out of my 36 ways that I could have a probability, or 18 out of my 36 ways that I could get an even number, sum. So my probability of F is 18 out of 36. Now I want to know if that's equal to the probability of F given E. Right? So E is this total showing is greater than 9, which means the only thing I'm looking at are 10, 11, and 12. So my sample space, remember this conditional probability is going to cut down my sample space. My sample space is now just going to be these possible sums. So there's one way to get a 12, two ways to get an 11, three ways to get a 10. So 3, 4, 5, 6 ways of getting a 10, 11, or 12. And then the probability that it's an even, well, there are 3, 4 evens. So what I get is 1836 simplifies down to 1/2. This simplifies down to 2/3. Those are not equal, so these are dependent events, which makes sense. All right, if we're saying, that we're going to make sure that we've got a sum that's greater than 9, that's going to totally change what my other probability is. So those events are dependent upon each other. Now, for part B, let's have E be that a 3 shows on the first die, and F be that the total is even. All right, so I'm going to find the probability of F, and I want to know if that's equal to the probability of F given that E has occurred. So the probability of F that the total showing is even, all right, that's the same as above, 1836. And then for the second part, we know that we've got a 3 showing on the first die. So that means the only things we're interested in are 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, and 3, 6. All righty? So we've got 6 possibilities there. And of those 6 possibilities, how many of them are even? This one, and this one. So there is 3 of those. So if I simplify those both, notice I get 1/2 is equal to 1/2. Since those are equal, these are independent events. Okay, so anytime you want to find out if something is dependent or independent, you just set these two things up, and then if they're equal to each other, you have independent. If they're not equal, you have dependent.